All right, let's start section 1, functions and their graphs. Definition: a function f from a set D to a set Y is a rule that assigns a unique single element f of x in Y to each element in D. Basically, this is mapping. We're giving it an input. We have some sort of machine or box here is the way I like to think of it. We give it some sort of input, and then it gives us some sort of output on the other side. And so that's basically what these functions do. They map from one thing to the other. This could be, again, like the way I mostly think about this is just, we have some sort of machine. You give it a bunch of ingredients, and out the other end comes whatever. Say it was a machine that made you dinner. You give it all the ingredients for dinner, and then it maps it out to the other side to whatever it was supposed to be, spaghetti or something like that. But it's that kind of an idea. We're going to give it some sort of number or numbers, and it's going to output a different set of numbers or even vectors later if you go far enough into the math here. So basically what we first have is a domain set. That's this over here. This is all your possible inputs, and then they are each going to map. As you can see right here, it maps over, follows that line to a specific point in our Y set over here, which is the set that contains the range in it. It's our output values. And so each one of these will map over to a specific place over there in the range. And a function from a set D to a set Y assigns a unique element of Y to each element D. Okay, and that's our idea for functions. Next definition: every mathematical function has an associated graph. If f is a function with domain D, its graph consists of the points in the Cartesian plane whose coordinates are the input-output values pairs for f. So you input some value, it outputs another value, and then you find in the Cartesian coordinates where that actually those two values are and where they line up, and you make a dot there. So example, the graph of the function f of x equals x plus 2 is a set of points with coordinates x, y, for which y equals x plus 2. Okay? And so what we do is we have a y equals mx plus b, if you remember that, slope-intercept form. And in this case, it's y equals x plus 2. That tells us we're going to have a slope equal to 1 and a y-intercept equal to 2. And we could also go through, we had that, have that kind of old way you can do it, or you could go through and actually plug in points. So we might say, let x equal to 1, and when that happens, we will get y equals 1 plus 3, or y equals, not 1 plus 3, sorry. Y equals 1 plus 2, and then that's going to equal 3. And so we'll get the point 1, 3 is on there, and then you could do it with other values as well and keep kind of doing that. And we get the point 1. So let's say we come over 1, and then we'll be up here at 3. And then right here we get that point. We could have also plugged in x equals 0, and you'd get y equals 0 plus 2, which is just 2, and we'd get the point 0, 2, and that's also on our graph, 0, 2. And you could go through like that and just do it a whole bunches of times until you finally map out the line, or once you get 2 points and you know this is the line, you just connect them. Okay. The other way we would have been was saying, well, we know the y-intercept is at 2. That's this point right here again. And then we know the slope is 1. That means we go a rise of 1 and a run of 1. It's 1 over 1. And we could, go through and do it that old way. The next thing that we have are just some of these different types of graphs we may see. You should be able to recognize these ones. This is a constant graph. This is, say this has a value of c right here, right there. Then we essentially have the graph f of x equals c. And remember, f of x is just y. So we have that. And that would also look something like f of x equals 0 times x plus c. and we would have a slope of 0 right there, and it'd just be plus z, which is just a horizontal line. This graph is called identity, and it's called that because it's the graph of whatever you put in is what you get back out. So this is f of x equals x, or y equals x. Sometimes you see it. That's that one. This graph is the absolute value graph. F of x equals the absolute value of x. Didn't get that drawn very well. Hold on. Equals the absolute value of x. And that's this one right there, and you get that kind of V shape. The next one is quadratic, and that's going to be, this is quadratic, and that's going to be f of x equals x squared type graphs, when you have that x squared, and you can have all other kinds of stuff in there and get it moved around. This is a cubic graph, f of x equals x cubed. You need to make sure you know these ones. And then this is also, last one is our square root function. Okay, this is f of x equals the square root of x, just like that. And so make sure you really start to recognize and remember these ones, and make sure you're familiar with them, because they're going to show up a lot for us. So writing the functions, express the side length of a square as a function of the length d of the square's diagonal. Then express the area as a function of the diagonal and length. So what we have here is we have a square, right? We have a square, and what we're trying to do is look at the diagonal, okay? The diagonal, d, we're going to call that, and then we've got side lengths, s, it's a square, so every side has a length of s, and it's a square, so these corners are right angles. And so what we've been ultimately asked to do is express the area as a function of the diagonal length. All right, now we know how to do the area of a rectangle. Squares are actually rectangles, so we just do the base times the height. And in this case, the base is s, the height is s, and so we're just doing s squared. Now, we need to figure out a way to get this in terms of d instead of s. All right, we want it in terms of this d right here instead of s. So we need to figure out a relationship between those. If we look here, we should notice that this is a right triangle, and therefore we can just use the Pythagorean theorem to say that s squared, so plus s squared, the two legs squared, the sum of the two legs squared, equals the hypotenuse squared. A squared plus b squared equals c squared. And so this becomes 2s squared equals d squared, and that means that s squared equals d squared over 2. Okay? And that's good, because right here, back over on this side, we have an s squared, which means we can substitute that out, and we will get that s squared equals, s squared is d squared over 2. So we're going to substitute that over, d squared over 2, right, from right here. And there you go. That's our answer right there. A equals d squared over 2. We now have an equation for the area of a square if all we knew was the diagonal. Next, we're going to express the area and perimeter of an equilateral triangle as a function of the triangle side length x. All right, so perimeter, so we have an equilateral triangle. Let's see how I can do here. Equilateral. That's okay. We'll go with it. And so that means that each one of these sides has the same length, and we'll call it x, x, and x. And when we look at that, we have that right there. And the first thing they ask us to, well, they ask us to do the area and the perimeter as a function of the side length x. So perimeter, that's going to be pretty easy. The perimeter p is just going to be the sum of all the lengths of the sides, which will just be 3x. So that one's pretty simple. Perimeter, 3 times the length of the one of the sides, because all the sides are the same. Well, what about the area? Well, if you remember, the area of a triangle is 1/2 base times height. And in this case, we need the base and the height. Well, the base is pretty easy. It's right here. This is the base right here. It's just x. So immediately we can write 1/2 times x. But now we need the height. And so the height is going to be this right here. This length right there, that dotted line. We'll call it h for height. And we need to figure out then what it is. Well, again, if we look, this right here makes us a nice right triangle. Here, I'll highlight it in blue. We have this right triangle right here. Okay, and that right triangle, the blue is covered up by the green, so maybe I need to get rid of that green real quick. So there you go. There's that right triangle. And this little side over here, this is half of x. So it's x over 2, which means we can go ahead and use Pythagorean theorem again. And we can do the 2 legs squared. So x squared over 2 squared plus h squared is going to equal the hypotenuse, in this case, h or x squared. This one's the hypotenuse. It's across from the 90-degree angle side. So we have x squared over 2, or squared, I'm sorry, I put too many squares in there. We have x over 2 whole thing squared, which gives us x squared over 2 squared, which is 4, plus h squared equals x squared. And then here, in this case, we need to go ahead and solve for h, because that's what we're trying to find, is this h right over there. And so this will become h squared equals x squared minus x squared over 4. We can reduce this. We can make this 4x squared over 4, so they have the same denominator. And this will become then 3x squared over 4 equals h squared, which then ultimately just means that h equals the square root of 3x squared over 4. Now here we're talking about length, so I'm not going to worry about the plus or minus that's going on there. And I actually can reduce this just a little bit more, but I'll do it up over here because I kind of ran out of room right there. So this will be equal to, now we're going to substitute in for h. Here's what h equals. So we'll put square root of 3x squared over 4. Now you may notice that I have an x squared under a square root, and I have a 4 under a square root, which means I can actually take the square root of those two things. I'll have a square root of 3. The x squared becomes an x, and the 4 becomes a 2. And then these all are multiplied together. So I can do 1/2. If I multiply the denominator together, I'm going to get a 4 in the denominator. I have an x and an x, so that gives me an x squared, and then I have a square root of 3. And that's pretty much going to be it right there. And there is our equation for the area of an equilateral triangle just based off the length of the side of the equilateral triangle. All right, next we want to look at, real quick here, interval notation. We can use interval notation to describe domain and range of a mathematical function. Here are some general examples of interval notation along with some basic practice exercises here for you. So first, you can see up here, interval notation. Whenever you have parentheses, it's going to be not inclusive, so that's like this example here. If you have a brackets, it's going to mean it includes the value that the bracket is around. So let me zoom in so you can make sure you can actually see the difference there. See, these are parentheses and these are square brackets. So in this case, in the first one there, with the parentheses, A and B would not be included as possible values. It would be just between A and B. And then in the second one there, A and B would both be possible values. You can also write this in set builder notation, where you're basically saying x is in, so this is our variable here we're looking at, so it's a set of x's such that, that's what that vertical line is, such that x is greater than a and less than b. And that's this right here. Whereas in the second one is x such that x is greater than or equal to a, that's the bracket that means inclusive, or x is less than or equal to b, again the bracket. And then you can graph it like this over here. You can put the brackets. Sometimes instead what you might be more used to than the brackets in parentheses on the number line might be something like this, where A and you put an open circle, and B you put an open circle, and then you fill it in between, or that's fine. And then whereas for this one, when it's inclusive, you put a closed circle at A and B and then darken the line in between. Those are going to be fine too, either one. Just make sure you know that they mean the same thing, whereas here they're putting the brackets to mean inclusive of A and B, but you may be more used to the open or closed circles when doing this. So either way is fine. So let's take a look here at this one. Here, what you also have to be careful of, sorry, I'm going to point this out here, is anytime you have an infinity, a positive or negative infinity like that, it's always going to be a parentheses. You can't include infinity. We can't even really define it as a number. It's more like an idea. So we can't include it, because whatever you're including, then there's always going to be something bigger than it. So no including infinities. Don't put square brackets around the infinities, positive or negative infinities. They're always these parentheses. So let's take a look at this one. X such that x is greater than or equal to -5 and less than or equal to 5. So we can write this with our interval notation. This would just be inclusive of both because of the or equals to, -5, comma 5, and then a closed bracket, because we are going to both of them. They're both included because of the or equals to sign. Then we could also write just as our interval or our number line. All right, we can do that. We can start here at -5, and again we can do the closed circle. I kind of like that better myself. All the way over to 5, again closed circle, and then we need to darken in between so we know that that's where it goes. The other thing you could have done was actually just put in the square bracket there too, if you like that. That's fine as well. 0 to infinity, this one's already written in the interval notation. So if we were going to write it in the set builder notation, x such that it is going to be greater than or equal to 0 and then less than infinity. We can't be less than or equal to. You can't have the equal to infinity part. So again, that's always got to be, you can't have that there. So then if we were drawing this in our number line, we just let that go on out forever. Here is 0. We are equal to 0, and then we need a dark line going out here saying that this is the way we're going. Okay? So something like that. And that would work. Okay? Domain and range. Not sure why I had that blank page there, but we can determine the domain and range of a function algebraically or graphically. The domain of a function is the value of x for which the function is defined. So these are basically possible values we can do. When we're thinking of that, what I was talking about at the beginning, where we have a machine and we input something into it, basically these are values that our machine can actually do something with. You want to be careful because sometimes it can't do anything with it. So like if I have a machine that makes you dinner and I hand it nuts and bolts, it's probably not going to be able to make me spaghetti out of it. That won't work. So for that specific machine, our spaghetti making machine, then it's not going to work. So there are functions such that where you try to plug certain values in and it just doesn't work. It can't give you something that we know how to do anything with. It can't give you anything that's defined. So we have to be careful about that. The range of a function is the values f of x equals y, obtained by inputting elements from the domain. All right, so you input values, you get things out. So things you have to worry about that are not defined as real numbers, first off, are complex numbers. That's going to be square roots of negative numbers. So complex numbers, that's a square root of a negative number. Dividing by 0, So some number, and then we end up dividing by 0. We don't know how to do that. And then we also don't know how to take the log of a number that's less than 0. So those are our three main things we're going to have to worry about here in this case. So f of x equals x squared. In this case, there's nothing that's going to make us take the square root of a negative number. There's no square roots in it at all. There's no division in it, so we don't have to worry about dividing by 0. And there's no logarithms, so we don't have to worry about taking the log of a number less than 0. Therefore, our domain doesn't actually exclude any numbers, and we can say our domain is negative infinity to positive infinity. Our range, on the other hand, is the numbers we get once we plug this in. Now, you should be familiar with this graph. Starts at 0, 0, 1, 1, 2, 4. Did I get that right? Yep, 2, 4. And it'll go something like that. And then this is curves up around like that. And so anyway, we get, well, that wasn't a very good line, but anyway, it curves up like this. And we get a parabola. And if we look at that parabola, we can see that it's never going to go below 0. So by looking at the graph, we see that it never goes below 0, but it does get down to and include 0. So I put the square brackets. And then it just continues out to positive infinity for the y values. But we can't include infinity. All right. So the domain, we're looking how far it goes side to side. For the range, we're looking how high or how low it goes, like that. Okay, I'm going to erase those so they're not confusing. All right, next, let's look at f of x equals 1 over x. Here, we do have to worry about division. So our domain cannot include x equals 0, because at x equals 0, we get 1 divided by 0, and we can't do that. So we don't want that. So we can't have x equals to 0. So our domain is essentially going to be written like this. We can't have x equal to 0, so we can go from negative infinity all the way up to 0, but we can't include it. And then we have to do the union, right? Union, so we go negative infinity all the way up to 0, and it's kind of like an and, that union, and we can go from just above 0 out to positive infinity. But we can't do anything else in between there. We can't do, right there at 0. So we have to break it apart like that. Next, we've got the graph for this. This graph should be something you're going to get familiar with, and it's going to look like this. Okay. It's going to look like that, and then it's going to look, it's going to look then like this. Okay. So it's going to look something like that. Just a quick little sketch. I actually should have gone through the 0.11. So let's call this 1, 1, negative 1, negative 1, and this is 1, 1. So I kind of messed it up there a little bit, but it should look something like that. These are hyperbola. It's a hyperbolic graph, and there you go. That's one that you should also become familiar with. The next one is y equals the square root of x. Here, we cannot take the square root of negative numbers. We don't know how to deal with that. It gives us a complex number. So we're not messing with that. So the domain is going to be everything from 0. We can take the square root of 0. It's 0, but we can't take the square root of anything below it. So we can include 0 and go on out to infinity, just like that. And then our range, and I just realized I forgot to do the range on the last one, so I'll go back and do it. Our range, well, when you graph this one, it starts at 0, goes up, up, just something like this, like half of a sideways parabola, and it looks like that. And again, we can start at 0 and go on out to infinity vertically. We don't go below 0, and this will just keep going up and up and up and up all the way to infinity. So it'll go up to infinity and starts from 0. Over here, our range, should have written this one. Notice again for the range, what can we get vertically? Well, we never ever cross this line. We're below it. Over here on this side, we're below it, and over here, we're above it. But we never cross it. So we never get to the value y equals 0, which means we can do the same sort of thing. We can go from negative infinity up to 0, but not include 0. And then union, we can go from 0 up to infinity. So it's the same as, the range is the same as the domain in this case. And so that's, kind of a couple examples where the domains and ranges were the same for each other. This next one, y equals 4 minus x. I'm going to let you try this one. Square root of 4 minus x. You try this one, see if you can figure it out, and I'll finish it off in the notes that you'll be able to look at and find later. Same thing with this one. I'm going to let you give that one a try, and then I'll put the completed version of it in the notes. And again, this one, yep, same sort of thing. Think circles here, or half a circle, semicircle. Okay, now let's take a look at the vertical line test. Recall that the vertical line test is used to determine if a graph represents a function. The test fails if you can draw a vertical line that intersects the graph more than once. Remember, for a relation to be a function, each input must have a single output. So you can't give it a value, you can't plug something in and have it give you multiple results. So if you look here in this first picture, this is the vertical line test, and it's hitting it twice, right there and right there. So this is failing the vertical line test. So that's not a function. Whereas here, if we draw a vertical line, it only hits it the one time. This will pass. And again here, this, draw a vertical line anywhere on here. It doesn't have to be at that exact spot each time, but anywhere on there you draw it, it's going to hit it only once. And so this one will pass. And he only has to hit it in two places in one spot. So you could have like a graph maybe that did something like this, and you say, oh, okay, well, if I draw a vertical line here, it only hits it once. Well, that still doesn't mean it passes, because over here it hits it more than once, and therefore it fails. It only has to fail it once in order for it to fail and not be a function everywhere. Okay? Next, symmetry, even and odd function. A function y equals f of x is an even function of x if f of negative x equals f of x. So that just means that when you plug in negative values, you get the same thing as if you had plugged in a positive value. If I plug in 2, then it gives me 4, and I plug in negative 2, it also gives me 4. That's an indication that it is even. Now, you can't just check one specific number like that, because it'll work for 2, but if I plug in 3, I get 9, but if I plug in negative 3, I get negative 9 or something like that. Then all of a sudden, it's not an even function. So you can't just plug in one value to check. You have to check it for all values. It has to be true for every possible value of x. And the same thing for an odd function, has to be true for every possible value of x. And this one is, if you plug in a negative value for x, you get the negative value, f of x. You get a negative. So if I plug in 2 and I get 4, if it's an odd function, I plug in 2, I'll get negative 4. So it'll flip-flop the sign on your output when you flip-flop the sign on your input. And if neither one of those is true, then it's not odd or even. So the first example here is f of x equals x squared. We can check this if you just look at the graph. This is our friendly parabola right here. Okay, that's our parabola, looks like that. And you can see that across this, right, over here we have positive values, over here we have negative values. They're the same on the positives and negatives, and we can even go ahead and test this. This is how you would test it. You would do f of negative x, and that's going to equal, we're going to plug in negative x for x, right? And so we plug in negative x and get that negative x squared. This is kind of like if we had said, what's f of 3? We would have done 3 squared. We would have put the 3 in for the x, right? We're just putting in negative x in there. And then we get negative x times negative x. And negative times the negative is a positive, so this is just positive x squared, which just ultimately does equal f of x. So when we plugged in the negative one, we end up getting back just our regular one that we plugged in. And this is the way you have to do it. You can't do it with one specific number. And so therefore this one is even, because we got f of negative x equals f of x. Now let's take a look at this one over here. If we look at the graph of this one, this is that hyperbolic function, and it looks like this, and then it kind of mirrors over this way. All right, and you should be able to tell that when we cross here, if we're that wasn't a very good line. If we're looking across this, this is the positive side over here, this is the negative side over here, and you'll notice that wherever we plug in here, if we plug in, say, 1 or 2 or something, and we get this value here, we plug in -2, we're going to get the negative version of that. So this one's looking like it's going to be odd, where our y values are going to get flip-flopped. So let's try this. We can do f of -x equals, and then we plug in 1 over -x. We can bring that negative out in front. We get -1 over x like that. And that just equals negative f of x, which is what our rule was for negative or for odd functions up here. And so this one is odd. And that's, again, the way you have to do it with just x plugged in there, not a specific number. An even function is symmetric about the y-axis. So it's symmetric right here. It's like a mirror image of itself across the y-axis. Whereas an odd function is symmetric about the origin. We can rotate it around the origin like that and get, and it'll rotate around and end up lining up on itself. So it's symmetric about the origin. Okay? Let's take a look here. Let's check these to see even or odd. So I'll show you a couple of these. F of -x, that's what we want to try. We'll put in -x on the top. We'll put in -x. You see that squared, so you might be thinking, oh, immediately this one must be even, but we can bring when we square -x, we just get an x squared, and so we get an x squared minus 2 on the denominator, and we have that negative on the top, so that's just -x like that. We can bring that negative out in front like this, and that is simply the negative of the original function, right? This is the original function right here. It's also right there. So this is just negative f of x. That means that this function is odd. Okay? So let's try this one over here real quick. Actually, you know what? I think I'm going to leave that for you to try, and I will put the completed version of it in the notes so you can see. You can see the graph of it right there, so you should automatically know whether or not it is, but try working it out using just f of x's and see if you get it. And I'll complete it in final notes online. Here, increasing and decreasing functions. Let f be a function defined on an interval I, and let x1 and x2 be any 2 points in I. So if f of x2 is greater than f of x1, wherever x1 is less than x2, then f is said to be increasing. All right, I did not spell increasing correctly. Increasing. And if f of x2 is less than f of x1, where x1 is less than x2, then f of x is said to be decreasing. All right, kind of fancy way of just saying that if you're moving from left to right, if you're going uphill, it's increasing. If you're going downhill, it's decreasing. So if we look at, say, a function like this that maybe looks something like that, right? We could actually break this into intervals of where it is increasing and decreasing. So I'm going to pick these peak points just like this. And what we would say is that on this side, as we move from one point to another, say this is x1 over to x2, right? Moving left to right, as we move from x1 to x2, our f of x values, this value here versus this value here, this would be f of x1, this is f of x2, right? You can see this right here. And you see that f of x2 is greater than f of x1. So you can go about doing it that kind of way if you want to think of it that way. The way I think of it is I look at this and I say, hey, I'm walking left to right. If I was walking, right, I'd be walking uphill. So on this interval, this is increasing, okay? This is increasing here. On this interval over here, if I was walking left to right again, walking, I'd be going downhill. So this interval is decreasing, okay? And I'd be walking downhill this whole time. I'd be down, downhill. All right, maybe steeper at some places, but I'd be going downhill the whole time. And then again over here, as I'd be walking back uphill. So this would be an increasing section of the graph. Okay, so we have increasing and decreasing sections. Next we have piecewise defined functions. Here we've got the absolute value of x, y equals the absolute value of x, and we can define this as two different sections. Here's y equals x. So this would be equals y equals x whenever we're at x greater than or equal to 0. We can include it there, but we don't want to include it in both places. And then y equals negative x, that's over on this side over here. This is the negative x side for x less than 0. And so that would be our piecewise function right there. And that's our y equals, or our f of x equals that right there. Okay, so we can break it into sections where in each section a different function is defining the values over that part right there. Take a look right here. If we wanted to do this one, I'll do the sections in different colors here, or maybe I'll just go back and highlight them. But negative x for x less than 0, so we just did that one. This is x less than 0, so it's going to look just like that. And that's going to be this section over here, I guess. I'll highlight that in purple. There you go. That's that part. Then we've got x squared from 0 to 1. So x squared 0 to 1 is just a little curvy spot, right? It's the beginning of that parabola. And so that's going to be, we'll do this one in green, is that little curvy spot right there. It's supposed to be curvy. It's not much room there to show it very curvy. And then the last part is it just equals 1 for x greater than 1. So then we just have this constant graph the rest of the way right there, which would just be this part right here, which is this part right there. Okay? And that would be our three little sections. And again, I can write these in. This is negative x, this is x squared, and this is just equals 1 at each one of those little sections. All right, next we can have greatest integer functions, or floor functions. What this basically does is when you write it like that, you can see the little brackets. You know, they look kind of like this, where they have the bracket, like almost the square brackets, but only the bottom part is there. Essentially what it says is take the value of x, but always round it down. So if we're here, we're at 0, it rounds to 0. If we're at 0.5, if we're at 0.2, it rounds to 0. 0.5 rounds to 0. 0.9 rounds to 0. You're always just rounding it down, dropping it down. And then you get to 1, which rounds to 1, and 1.2 rounds to 1, and 1.5 rounds to 1, and 1.9 rounds to 1, and they all just keep rounding down. And so as you go through doing that, you floor everything. The next is the ceiling function. You can see it here. It's like the square bracket, but you only have the top part. And here, oops, I didn't do it very well there. I started to do the square bracket. It only has the top little notch part on it. Here, you're always rounding up. So if you're at 0, you stay at 0. But if you go to 0.1, you round up to 1. 0.2, 0.5, 0.9, they all round to 1. And the same thing here, then you get to 1, it rounds to 1, and then 1.1 rounds up, and 1.5 rounds up, and they all just keep rounding up like that. That is our ceiling function. All right, for what values of x is the ceiling of x equal to 3? And in interval notation, if we were going to write this, where does the ceiling function equal 3? Well, that's going to be right here if we look at the graph. Notice it's open on 2, which means we're not going to include 2, but it's closed on 3, so we will include 3. So in interval notation, this will look like parentheses 2, because we don't include 2, all the way to 3, and then bracket around 3 because we do actually include 3. Okay? All right, here, find the domain and graph of this function. Again, I'm going to leave this one for you to give a try to. It's a little, try thinking your way through it. What's going to happen on the positive side? What's going to happen on the negative side? And see if you can graph this. And then again, I'll put the answer up. I'll put the answer up on the notes you can see online. Okay, so that's pretty much it for this lesson.